Hello and welcome to the Stardog Academy Training on Performance. I'm Al Baker, Vice President of Enterprise Solutions here at Stardog. To let you know a bit more about me, for the past 20 years, I've helped organizations from the likes of NASA to top 5 pharmaceuticals realize their goals of getting the right data to the right people at the right time. Today, I'm going to introduce you to performance. In this training session, you will understand capacity and data inputs to provide Stardog with the right resources for optimal performance, enable self-diagnosis of a performance issue leveraging SPARQL semantics, including joins, filters, and optional operations, learn to read query plans and use them to identify query performance issues, and finally, review Stardog's tools and examples for debugging common problems. Let's get started. This section is about capacity and data. So let's start off with the system that Stardog is going to run on, and the resources that the platform needs to optimally operate. First, Stardog uses memory aggressively, and the total system memory is often the most critical factor in optimizing performance. It is often the first place to start, the first thing to check, and, if not monitored appropriately, the first area that a problem can arise. The second key aspect of the system is the disk space. Now, we use this for both the storage of the data, incremental transaction metadata as transactions are handled, and as well as a feature to handle memory overflow to answer particularly large queries. Now, going into the memory guidelines in a little more detail. First, we're going to look at the Java virtual machine, where we should have heap not less than 2 gigabytes. And for 32 gigabytes and larger systems, especially in the 50 to 60 gigabyte range, we can use some of the JVM parameters, as noted here, to provide optimal performance. Now, direct memory should be set higher than heap memory, except perhaps very small scales for the heap size going below the recommended 2 gigabyte limit. And the sum of these two settings should be around 90% of the total system memory. Now, as a data processing platform, we do not want to run other memory-intensive applications on the same machine as Stardog. This includes other dependencies that Stardog requires. For example, the Apache Zookeeper should be run on a separate system in the cluster environment. Likewise, any ETL components, including Apache NiFi or custom-built software, should also run on separate servers, leaving Stardog to have the optimally managed environment to run on. Now, the specifics on how much memory you will need will be determined by the size of the data that you plan to load into Stardog. Note that this does not include the virtual graph triples that will be in your total system, as most systems today have some data that gets loaded in, whether that's ontologies, reference data, or so on. And then many systems will have virtualized data over virtualized sources. And so the capacity plan here is for data that is only materialized or loaded directly in to the Stardog servers. Additionally, this capacity chart is subject to change, and we recommend that you go to docs.stardog.com for the most up-to-date version. However, as a general guideline, we can see here from a relatively small size of up to 100 million, the system will run in a typical environment, most likely in the tune of a developer workspace, with only 3, 4, 6, or 8 gigabytes available to allocate to that server. 100 million triples can be easily accommodated. As we increase the number of triples and going up to 50 billion triples, we see that the amount of memory increases. And again, a capacity plan aligned to the currently documented capacity availability in Stardog should be performed as part of any implementation. Moving on to disk usage, we're going to start with industry standard disk guidance. And as a data processing platform, we want to be able to read from disk as fast as possible. So we are going to prefer environments that offer solid state drives as the underlying storage means and avoid anything that can introduce latency. For example, having any part of the Stardog file system usage using a file system like NFS. In general, 1 million triples is going to require 70 to 100 megabytes of disk space, but this may be different on your individual system. Additionally, bulk load and creation time has a higher than normal usage as temporary files are created to speed up the bulk loading process. So our recommendation is to have essentially double the disk space available based on the estimated file database size of the number of triples that you're going to load into the system. Now, these database sizes, of note, will be summed up for every database in a Stardog server to get the total disk space requirement. Looking more specifically into the bulk load options, Stardog offers some features to speed up the database creation time for those large-scale datasets. Let's take a look at some of those capabilities. So first, we're going to prefer compressed data. So if we can compress the RDF data, which compresses very well, Stardog will be able to read the compressed data and load it faster. Additionally, splitting that data set up into multiple files and loading them into parallel will also run faster, as Stardog takes advantage of multiple cores on multi-core machines, both on the loading as well as on the index creation. There are a couple options that we can use to speed it up even further. First, if we are relatively confident that the RDF is sound, we can turn off the strict parsing option, which reduces some processing time during the loading process. There is also a specific memory option for loading very large databases, and we can use the bulk load memory option and then set it back after we complete the bulk load. Finally, we have the copy server side for copying files to remote machines. In general, we want to eliminate as much latency as possible to process some of these very large-scale datasets. Now, there are other options for loading data into a system. The first one is your typical ETL pipelines for extract, transform, and load. Stardog offers a specific one, Stardog ETL, currently based off of Apache NiFi, which can be done with parallel processing steps. Additionally, if the target architecture includes a cluster with the cache node feature, cache nodes can be loaded out of band for maximizing operational changes to running clusters. And then finally, pre-copying files onto the target systems and using the Stardog data add command with the server-side flag will process the files more quickly, again, eliminating any chance of latency within our data load pipeline. This concludes the section on capacity and data. This section is about understanding SPARQL evaluation. Now let's begin with asking the question, how does SPARQL evaluation work? Well, the SPARQL specification defines what answers should be using and the so-called evaluation semantics. This includes both the syntax as well as the meaning of processing the expressions within the query. This ensures that a SPARQL implementer will answer the same query with the same answer, regardless of implementation. Now, this query, for example, asks for all persons and their names who have authored an article and whose names contain the string Mary. It contains a single scope or group graph pattern, which is everything within the curly braces. And now let's see how the SPARQL semantics are defined. SPARQL evaluation is defined in a bottom-up fashion. It all starts with the evaluation of the so-called basic graph patterns, or BGPs. This term BGP is common, and it will be likely found within other documentation as well as this training. Now, in this case, we have BGPs highlighted in blue. These are a set of patterns that match triples, or really quads, as all triples will have some context within the store of the RDF graph. Note that the semantics are declarative. They define BGP matching through subgraph isomorphism, but they do not tell which algorithm should be used to implement it. Stardog matches every triple pattern individually and uses join to combine the results. But other systems could have other algorithms like graph traversal. In general, it doesn't really matter. Some join algorithms will work very similar to graph traversals. They'll have similar performance and scalability characteristics. So let's take a look at this query going bottom up and looking at the basic graph patterns. Now the match results move up and eventually become the final query results. However, the specification must also define what happens in between, depending on what else other than BGPs are used in the query. And so here we look at the BGPs. Moving up, we see one SPARQL feature used in this query is the filter. Now the condition in the filter is a substring containment check. According to the SPARQL spec, the filter is essentially a single argument function. It takes a partial query result, in this case the match subgraph produced by the BGPs, and either passes the result further if it satisfies the condition or eliminates it as a matching set. Further moving up, the next SPARQL construct is something which is used in every query, and it's called the projection. It's an operator defined by the list of variables to be included in the query results. It's also a unary function which takes a partial query result and eliminates all variable bindings, that is, name-value pairs, except for those of the given variables. In this example, it eliminates the values of the article value, as you can see here that we have person and name as our variables to include in the projection. Now this query isn't done yet. There's still one more keyword here, and that is distinct. Much like in SQL, eliminates duplicate results, and once that is processed, we can finally send the final results back to the client. Now this was a straightforward query, and let us walk through a bottom-up example, and everything followed a very linear evaluation. Now, not every query is going to be this simple. However, they will always be bottom-up like this. There are, for example, no correlated subqueries like in SQL. The graph of query operators is hierarchical, and there's a partial order, and it's acyclic. It always starts at the bottom, and results go through a series of transformations and filters till they reach the top. Now, database systems don't have to implement it this way, but the query results must always be the same as if they are computed in this fashion. So let's use what we've learned there and start to look at some problems in queries and understand what's going on. Understand the semantics is important because otherwise it's really easy to write an incorrect query. And it turns out that when a query is written incorrectly and returns something other than what you intended, it's often very computationally expensive. The opposite can also happen, but it's less common. So let's take a look at this query. The author wants to select editors of all journals and all preceding volumes in the dataset. There's one BGP here that matches journals and their editors, preceding volumes and their editors. It looks quite straightforward, and this type of query has been written often over the years and then questioned on why this type of query will run for a very long time on any system against a reasonably large data set and probably overwhelm the client with the number of results. Let's dig a little bit deeper and see what's going on. If we look closer at the BGP, we will see that it's composed of two disjoint parts. We've got two triple patterns that are selecting journals and their editors, and two triple patterns selecting preceding volumes and their editors. But these parts do not share a variable. This means that every combination of a journal A with its editors and a volume B with its editors is a valid match for the BGP. More formally, we say that this BGP matches a full Cartesian product of the set of journal editors and the preceding editors. So 100 journals and 100 volumes gives you 10,000 results. It grows quadratically. This isn't what the author of the query wanted, but unfortunately, this is a common error that even advanced users are prone to making. Now, whether it was intentional, occasionally a variable name is supposed to match up, but there was a typo and it creates this situation. So this is the trap that is really easy to step into. All right, so how do we fix a Cartesian product query where we want to select editors of all journals and all preceding volumes? Well, we could do a straightforward union of these. We knew that in this case, the editors, in fact, were not disjoint. We could also provide a natural join by updating the variables. And this query will now run appropriately. So let's talk about selectivity in variables. Here we have another example of doc with 10 offers, which appeared in 100 books, and the results grow combinatorially. And we see here that we have doc creator author, and then doc book title book, doc see also, see also. Now, to improve the selectivity of this, we want to match only asserted edges, not combinations. And so here we put in a class, doc is a document, and then use that to find the additional edges. A good way of testing if you have the selectivity correct is we can run a construct query as a version of this update first before we run the update. This concludes the section on understanding SPARQL evaluation. This section is about operation considerations. Now that we understand the SPARQL evaluation semantics, let's dive deeper and understand all the operations that Stardog is going to perform to answer the query. And we're going to start with the scan. It's what we use to read data from an index, where the index sorts triples in different ways, and we select these index based on the constants in the query and the join variables. Now, Stardog has several indexes. You'll often see these as subject, predicate, object, context, with the first letter indicating the sorting order. And these index orders will then be identified by a series of letters. For example, SPOC would be subject, predicate, object, context, but we might also have another index for predicate, subject, object. Now we have multiple different types of scans. And as we see here within our query plans, the scans might go over various sets. So we have scans of all triples, we've got binary count indexes, and we can scan a unary count index as well. You can see where the variables are placed in each one of the positions. Now, scan is one type of what we call a node, and these are the operational nodes within the query plan. So we have scans, joins, unions, filters, projections. We've talked about some of these during the SPARQL evaluation semantics. And now we'll see how these are combined within a plan to answer the query. Each of those node types will have some basic pieces of information like cardinality, how many solutions will be generated by executing that operation, a sort, which variable by which solution will be sorted, and nodes might have 0, 1, or 2 children based on the node type. Looking specifically at joins, we have joins which result from 2 other nodes, for example, scans, and the solutions from both nodes should agree on the value assigned to the shared variables. For example, outer joins, right solution may contain a null value, and we could have different kinds of join types used based on the children nodes, and we'll see some examples of that. Stardog implements several different types of join operations. We've got the merge join, which has both nodes sorted by the same variable and skips unrelated solutions. The hash join, which materializes the right operand in the hash table and iterates over the left. Or the direct hash, which iterates over the left and computes the right operand on demand. And the loop join, which iterates over right operands for each solution on the left. Some commonly used plan types that you'll also see within a query plan are union, where we return all solutions generated by the children. We saw that earlier when we fixed our Cartesian product query. Filter, which filters child solutions based on an expression. Bind, which adds another mapping to a child solution. Projection, which we also saw earlier, which keeps the selected variables in the child solution. And sort, which retrieves all the solution from the child and sorts them by a specific variable. So now that we know the piece parts, let's start walking through some examples and see how they're applied. So we're going to look at 2 SPARQL patterns in the same group that are joined. Now for SQL users, all inner joins are natural equijoins. And we're going to use the easiest example here about looking at values applied to data. So the first thing that we're going to do as we look at the x, y variables is follow B to the first match. And then we see a second match. Now we can follow D for our third match. And we wind up with these tuples that are called solutions. Now, SPARQL query execution is basically processing bags of solutions, which include things like filters and joins, etc., until we come up with the solution that fully satisfies the query. So the first issue here we can have is when a join key does not have a value, because join condition is always satisfied when the joined variable is unbound on either end. And this could have an unintended consequence of a large number of results than expected. So we can see here the undefined matches this and adds an extra result to our query that we may not have intended. The next thing to look at is optional for joins and unbound join keys. So optionals are similar to left outer joins in SQL and deal with missing data. Looking at this query, we have person lives in city, city is located in country, and then country has a name. A typical 3-hop query. But what if in our data, both located in and name triples can be missing? Can we use an optional to still make these hops and make it a relatively high-performing query? So first attempt is to put the optionals on city, located in country, and country has a name. However, this introduces an unbound variable. In this case, country name may not be bound because the optional from city located in country could not be bound. And so we wind up with an additional join. And this is the basic SPARQL algebra. There are tools that can be used to see this in addition to the Stardog query plan itself. So Inspecting this algebra, let's do our bottom-up analysis. First, we're going to join on city with no nulls, and then second, join on country that has nullables. So inspecting this unbound predicate, for every person living in a city without a located in triple, the query will return all countries. And second, even if the data is perfect, dealing with nulls slows down the join a lot. For example, the standard hash join won't work, and Stardog will have to pick a different operation. And this will often show in the query plan. So our fix here is going to avoid the correctness issue, and we are going to move the second optional into the first optional. So if a person lives in city, then optionally, that city could be located in a country. Then if that is bound, optionally, the country could have a name. Now, there might still be some performance issues here, having to deal with the nulls that are found as those optionals are operated on. But now this query is optimizable, and the query planner can do something with it. Moving on to joins on variables introduced by bind, we see that SPARQL allows for adding new variables to solutions. For example, we could bind x plus y as z, and we could even use them in join keys. However, we need to be careful, as these SPARQL expressions can raise errors, like type errors, which make the target variable unbound, and these may not be visible to the client. And they can even affect performance even when errors don't happen. So using the bind and performing additional computations is something to be careful with as we're designing our SPARQL queries. So let's take a look at an example. Here we have a company that employs a person, and now we're going to bind a new employee IRI by concatenating the URN employee with the string after person and include an additional colon there and then make it an IRI. So in this case, we want that person variable to be a string as it's being passed to a string function so that we can then turn it into an IRI. So what happens when we evaluate this expression? So first observation is this is a kind of data integration query where we have an IRI for the company and we only have some string information about the person, and we want to turn that into a proper node in the graph that we can then use with additional statements. And so our additional statement here is that once we have that employee IRI, we can say that IRI is a type of employee. And the result is linking the company employee data to instances of employee. However, another observation is what happens if the person variable is not a string literal? That means our variable employee ID won't be bound. And therefore, this query is going to return all employees for that person. So thinking about that, this might be a good time to fix the data, or we might need a more complex query with type checks, or bound it with filters. This is a good time when thinking about fixing the data on were there things like shackle constraints that made sure that we didn't have values in here that were not string literals, like employee IDs as an integer or something of that nature. The next thing to look at is comparing joins versus equality filters. This is another common practice. So we're going to look at two potential queries. Here we have our person lives in city, and city is located in country. So we have a natural join here on the city variable that is in both the object position on the first line and the subject position on the second line. Now the alternative query below is similar. However, we're not using the same variable in that object position and subject position. Instead, they're different variables, and now we're going to assert equality within a filter. So let's think about this. Well, we have the first issue is that the optimizer must figure out that these two different variables will bind to the same value in every solution of which the BGP passes the filter. That means that we are asserting the equality higher up in the evaluation semantics. And that's not always going to be true because we could have nested filters or other graph patterns. Additionally, the filters and optionals have special semantics in SPARQL. And so the optimizer has to do additional work to do this evaluation. The second issue is the optimizer cannot convert this to a join because company or employer may bind to different RDF literals, and they may still be equal or not equal. And this may be optimized if the SPARQL engine knows that it's impossible for other reasons. So our recommendation here is that this is an anti-pattern. Having the different variables in those positions to perform the join via an equality filter provides too much differences in the evaluation semantics and limits the Stardog ability to optimize that query. So performing a simple adjustment of renaming the variables such that they naturally appear as a join of having the variable in the object position on one and the subject position on the other is the recommended fix. So with many graph patterns and expressions, the order of joins will be the next thing to consider. So the good news is that SPARQL engines are pretty good at reordering inner joins. In this example, we've got person lives in city, city is located in country, country has a name. So we can evaluate this in different ways. Well, first we could join the lives in with the other join of located in name, or we could reverse that and join lives in located in first and then join that with name. Now, some engines can fail to pick the optimal order, but they can try. And this is a classical query optimization problem in databases. So the first thing to consider here on the reordering of joins is optionals. Introducing an optional makes it more difficult and error-prone, meaning the query planner may decide not to reorder the join. So in this case, it can often be executed as is. So in our example here, we're going to have a join of the outer join lives in and located in with name, which may or may not be optimal. So the join order optimization is a search problem where the search places all equivalent join orders, and the goal function is based on cost. So the search space is easy for inner joins since all permutations are valid, and we just saw that in how we can reorder the joins. But most of that fails for outer joins in general because there's no straightforward procedure to enumerate all combinations, and then the search space becomes hard to define. And so it's incumbent on us as query designers to introduce optionals in the correct place when we're defining a query. So let's take a look at how we define those optionals. So first, moving patterns in or inside the optional are not always equivalent. And we can also specify this in multiple ways. We can introduce another pattern. We can put the optional before another pattern. We can have multiple patterns and then limit the optional. And this introduces a question. Can the optimizer freely move the optional patterns up and down and still result in the same query? First, let's look at this example where we have values of x, an optional value of xy, then another values of y, with optional in the second line here. So we can evaluate this query, and we have x bound to d and y bound to e. However, what happens if we move this optional? Well, if we move it to the bottom of the query, we get different results. And so really we shouldn't be moving the optional. It should be on the designer of the query to put the optional in the right place such that the variables are bound appropriately and the expected results can be made. So let's summarize optionals and how they're treated. Firstly, some optionals can be optimized, and Stardog will push those selected patterns and optionals when it can, but it must be able to detect that semantics are not going to change. So what does this mean for you as a query designer? It means placing optionals is risky, and so we must think carefully about where they are placed in our queries. And in many cases, that means they should be pushed to the bottom of the query, as we saw in our example here. And a good hint to think about is that optionals never really decrease the number of results. Now, as we mentioned, handling optionals, join order optimization, these are areas of common database architecture, how query planners are designed, and how different databases implement it. In fact, some SQL engines can often rewrite outer joins into inner joins. But this is a leading area that needs more work on bringing theory to practice. For those interested in the lower level details, there are many papers out there, and we recommend taking a look at canonical abstraction for outer join optimization, which is a SQL-related paper. The next operation to look at is service. So service is another kind of graph pattern, and it has the same evaluation semantics, meaning that there will be bottom-up analysis within the service pattern. Now, service results are joined with the rest of the query, but are uncorrelated. And there are many challenges to get a service query executing the way you want and expect. First, in general, there are no selectivity statistics, as the far end is not communicating with the Stardog node answering the query. Second, because we're reaching out and querying another endpoint, the reliability of that endpoint can be in question. And we're also going to pay the data transmission and ingestion costs on the data that is coming back. So our first observation here is that most optimizers are going to try to constrain the service invocation by local bindings. So we want those local bindings to move into the service pattern and add some constraints. This will limit the amount of data that we're going to pull back. But that can fail for various reasons. We can pick the wrong local pattern. The query plan that we were expecting may not be what got generated, so we need to check the plan. And typically we're going to place our local patterns, in this case binding person, in the same equivalent service. Those remote endpoints may throttle rapid requests. For example, limits on the join patterns could help. So the behavior of those far-end SPARQL endpoints, their reliability, if they have throttling, and other factors can change the nature of how the service graph pattern is going to behave. This concludes the section on operation considerations. This section is about query plans. Query plans are a tree of plan nodes. We looked at the various types of nodes in our previous section. Each one of these nodes is going to generate 0 or more solutions, where a solution is a mapping from the variable that was expressed to the value that was found. This execution is going to be bottom up, as previously discussed, and those solutions generated by a node will go up to the parent node for further processing. Now, solutions are generated while the client is consuming results, which means that there can be streaming results going back to the client. If we look at the Stardog query engine internal architecture, this will help us understand all of the piece parts that go into forming a proper query plan and optimizing it for execution. On the left-hand side of the screen here, we have our query and our triples. The triples have been loaded in prior to the query. And once the triples are loaded in, a mapping dictionary of a key value store will map the URIs to values. And an update manager will see the updates or these new triples being added to create the various indexes that we have seen, such as subject, predicate, object, context, and so on. These indexes will then be periodically updated and have statistics on the various patterns and profiles within them. When a query comes in, the query optimizer will pull in the mapping dictionary and those statistics to create a query plan. Once that query plan is generated, the execution engine will use it, using those nodes, performing scans, performing the algorithms like merge and projection, until ultimately producing a result of solutions that will get sent back to the client. Now, the query plan is something that you can get out of Stardog. Within Stardog Studio and within the workspace, before you run a query, you can show the plan and get it in both a visual, as seen here, as well as a textual representation. It is often the textual representation that will be copied and pasted and sent to support if further assistance is required on understanding a query plan or for recommendations on how to correct a performance issue. So what is the difference between query algebra and a query plan? Well, SPARQL defines semantics using algebra expressions for all SPARQL constructs and specifying what their results should be. There's expressions for all basic constructs in the language, such as BGPs, joins, unions, filters, aggregations, and so on. An implementation like Stardog is free to implement these expressions in any way it wants, as long as the results are as specified. So Stardog implements triple patterns with index scans and BGPs using joins over those scans. There are multiple join algorithms with different performance characteristics. Some are going to be faster, but require some conditions as inputs, and others could be slower, but are more generally applied. So the algebra is useful for understanding the query semantics, but it's independent of the actual implementation. The query plan will be how the engine evaluates this query. So query plans in Stardog. Well, Stardog implements the volcano model, where each algebraic expression corresponds to some executable operator. You can see this in the Cascades framework. This means that triple patterns will be evaluated as index scans, BGPs, joins over index scans, and so on. The benefits is that this is a very extensible way to build a query plan, the plans are easy to read, and the information on SPARQL solution flows bottom up. So we can look at the plan and follow the same bottom up process as we're looking at for the query semantics. So using our Cartesian product query from earlier in the training, let's take a look at the query plan that gets generated for it. So we have our BGPs, and as noted, these result in scans. Now we have to join each of the scans for each of the patterns expressed. So we have two merge joins, one for in-proc and one for journal. Then there is a nested loop join, as the combination here can be valid for all possible combinations as per our Cartesian product. And once that executes, we have our projection. So looking at that nested loop join is a good hint that we have a Cartesian product. And you'll notice that there is no variable on the nested loop join. We are going to join over both of those sets. So when looking at the query plan, we want to think about the query pipeline, or the most efficient way for every operation within the plan to execute in a streaming fashion. Now, this means that efficient query execution is streaming when we have index scans that match some data and generate partial results, and then are immediately processed further, for example, joined or filtered, and then returned to the client. Now, the key here is the first results are processed before all results are generated. This is called the query execution pipeline. It has benefits of being lazy, so we can execute some at a time, low latency, and minimal resource consumption, as Stardog does not have to have the intermediate result sets within memory. So when does the pipeline break and queries start to become slower? So the first observation to make is that not all SPARQL query processing can be done in a streaming fashion. And the pipeline is going to break when we start having to accumulate results for processing before sending them along. So examples of this and key things to look for in your query plans will be hash joins, where we have to build a hash table, sorts and order bys, where we have to have the data in place to perform the algorithm, and then aggregations like count, min-max, sum, average, and distinct. Now, the results of a pipeline break are going to be increased latency and memory pressure on the server, as we have to start accumulating these results to process them. In Stardog, and also generally, the fastest join algorithm is typically the merge join. This algorithm is streaming, and it joins on an input key as they become available, but it requires both input streams to be sorted on that join key. Now, Stardog indexes the data rather aggressively, so when joining two triple patterns that the condition is usually true, and we can see how this works in an example. It's useful to regard outputs of both triple patterns as relations. So the published relation has columns author and journal, and the editor relation has columns journal and editor. Now the merge join computes the results in a zigzag fashion. It starts going down the left relation published, and for a result there, it runs a binary search over the sorted right relation, thus skipping over large portions which have different values of the join key, as shown in gray. And this could be megabytes of data. We have a single value here, but for large data sets, this will be significant. When the match is found, the joined result is generated as seen in the right-hand side table. If the current value of a join key on the right, for example, Journal of Machine Learning Research, is greater than on the left, it runs the binary search over the sorted left relation again till the match is found. And when it is found, the next result is generated. And this process repeats till one of the relations is scrolled till the end. The merge join is efficient because disk I/O is low, because when the data is indexed, it's usually possible to seek to the row, or the triple in this case, and this has a particular value on the join key without reading all the data in between. So results are streamed as inputs are coming in. There's no memory pressure, because as the results come in, we send them back out. And there's the low disk I/O overhead. Unfortunately, in complex queries, there's usually more than join. There's a whole tree of joins feeding results to one another, and it's not possible to ensure that every join operator always joins inputs which are sorted on the join variable. Though, the optimizer should try to satisfy that condition as much as possible. In those cases, either data is sorted in memory, for example, using a sort operator, or other join algorithms are used, for example, a hash join. It also requires a shared variable, but it breaks the pipeline. And let's see why on the same example. First thing the hash join does is it picks one relation and creates a hash table out of it. Each row in the table is a row in the relation, in this case editor, but also has the key column, which contains the hashed value of the join key, in this case, the value of the journal variable. We say that this relation is hashed on the journal variable. It does so to support efficient lookups of rows having a particular value of the join key. Now, since the relation is not sorted, the next best thing is the hash table. The important thing here is that the join cannot start producing its results till the hash table is built, and this finally has broken our pipeline. Once the hash table is built, the join proceeds as follows. It iterates over the rows of the left relation, in this case the published, and for each row looks up rows on the right which have the same value of the join key. It's a lookup in the hash table, and once it succeeds, it generates a single result. The algorithm does these lookups for every row on the left. Some lookups succeed, and they find the best match in the hash table, and others don't. So to summarize, performance problems associated with hash joins are fairly similar to other pipeline breakers too. And we can have performance-related issues like latency, where the hash table has to be built before the first result is produced. This results in memory pressure. Depending on the size of this in-memory data, we could have possible spilling to disk, which is going to be slower than in memory. We have the higher disk I/O, where one relation is fully hashed and the other is fully scrolled. And we're addressing a lot of random memory access. These are typical for other pipeline breakers as well. So think about the sort operators, hash minus, anti-joins, group by and distinct. And a lot of the performance analysis, whether done by the Stardog support team or customers, comes down to finding the pipeline breakers in the plan, or generally bad join orders, where we're doing an expensive join before a selective join. So how do we fix a slow query? Well, first, engine-specific tools help the analysis and the correction of a slow query. And we can do this with some query hints, which tells the optimizer what to do, though the optimizer may still ignore it. Things like the join order to pick. The general tactics we can use here to work to improve performance. One is to look at some subqueries for defining a join order and pushing distinct down in the plan, and move selective patterns around. As noted, having the selective pattern executed prior to a more expensive join is going to speed up the query and provide results quicker. So we just learned how to fix a query. Now let's use this in an example. So we have an author, Paul Erdos, and it's a query from the SP2B benchmark. And we want to find all first and second degree co-authors, and essentially we're going to iterate over his papers, get the authors, and then look at those authors for other papers. So optimizing this and fixing it will not quite align with how it's defined according to the query's SPARQL algebra. And we can take a look at that. So taking this query and looking at its algebra, we see a BGP triple with the name, union over two filters with additional BGPs and many other triples. But Stardog is not going to do the union of the author at the top. In fact, we're going to push this as far down as possible, as well as all splits and filters as we can, so that we can have very selective merges going all the way back up. We can also rewrite this manually, putting the triple in, or BGP directly in, and rewriting it as the subquery as recommended in how to fix a problematic query. The objective here remains the same. We want to push that selective operation as far down in the query plan as we can. So, some other general tips to consider. First, project only necessary variables. If you come from a SQL background, things like select star or listing all the columns are generally not helpful. And if we know what we want, we should just express that and project only those necessary variables. Second, we want to avoid order by in subqueries unless there's a limit, as this is going to break the pipeline and bring in that data to be sorted and ordered. We want to drop unnecessary distinct, for example, in queries with group by. If the data is already distinct, adding the extra distinct keyword here only decreases the performance. And then we want to be very careful with property path with star. So using things like zero length paths or using them in a sequence. And in many cases, this can be replaced with the plus operator. And so again, thinking about, can we have a streaming pipeline in our query plan? And then finally, full text search using Stardog's full text search feature is often faster than using filters with regex trying to match string literals. And so turning on Stardog's full text search adds another index, which Stardog can then very quickly take advantage of in its query plan. So the takeaways on query plans. In the ideal world, the engine always picks the best plan, but we don't live in the ideal world, and queries can have different plans depending on how the data is laid out, how the query has been expressed, and even things like the flexible schema that RDF affords, meaning that picking the right join optimization or the right operators in the plan is not always straightforward and is in fact classified as an NP hard problem. So these optimization algorithms operate under uncertainty. We have to generate statistics, perform cost optimizations, and every query optimization problem boils down to a poor selectivity estimation. And so thinking about selectivity in our queries is always a first thought that should be had. Now, some query plans will be suboptimal, particularly when you see the join tree involved, and vendors work daily to improve this. As Stardog releases come out, query performance and updates and how to pick optimizations are a common enhancement present in the platform. And query developers will sometimes need to give hints to the optimizer. And so if you know that the data is going to be laid out in a particular way and you want the join to occur in a particular fashion, then taking advantage of some of Stardog's query hints can be a way to very easily improve performance and have the result of higher performing query plans that get generated. So our general advice, every decision to write the query should be based on evidence. A query plan, profiling, how many times did we run this query, what were the results, taking those measurements. We want to think about why the query is slow and try to prove or refute them, especially as queries become complex and we're navigating the graph. We want to run different parts of that query. So take apart the query and start to look to see, is this part of the query selective? Am I pulling in more data than I need? And am I assembling this query in ways that break the pipeline? So thinking about aggregates, things like count star. And don't assume the query plan is telling you what you think is happening. You never want to make performance-oriented changes just because they seem to work. We want to understand why. We want to understand that query plan and how adjustments to our query reflect on that. And it's better to deal with suboptimal queries than those you cannot understand. So starting out and building up that query, understanding each part, assembling it over time, and understanding each part of the query plan that gets built is generally good advice to have a repeatable process to develop higher performing query plans. This concludes the section on query plans. This section is about tools and examples. Stardog offers many tools that we can use to understand our queries and exactly what the query engine is going to do. So our first tool is explain. Now this is something that can be done in Studio or the command line. Here in the command line example, we are going to explain a query. And from here, we get the query plan. You'll see, as discussed in the performance training, that we have our various nodes in the plan, from projection, bind, merge join. We read it from bottom to top. We look at our cardinalities and how selective it was, and we can understand how this query is going to be executed. Now, we can use the same explain command to detect slowness in the queries. So here we have one of those unrecommended anti-patterns where we are using filter equality to effectively perform a join across these two BGPs. Looking at the query plan, we see the loop join as our key marker for a problem, and we see the cardinality of 293 million possible solutions compared to the 17,000 in the original scans. So finding these explosion of cardinalities is typically a first sign of where your query is slowing down. So rewriting our query, we change that from the filter equality to performing a natural join by having the variable in both patterns. And now we see here that the type of join has changed. We now have a merge join, and the cardinality is 704,000. This is a drastic improvement, and we get the streaming merge join as a benefit. As we look at those query plans, what are some common signs of a problem? Well, first, very large cardinalities, especially higher in the tree. We want that selectivity to limit the cardinalities. And so if we have in our bottom up semantics a highly selective set of scans at the bottom, then we want to limit those very large cardinalities. Second, we want to avoid a loop join and make sure that our joins have appropriate keys that can be followed. In the event of an empty plan node, that could also indicate that we're going to have a join that is not what we expected. And then finally, the large cardinalities for non-streaming node types. So sort, hash join, distinct, aggregate. Finding ways to either limit the amount of data or perform a more selective query when you must do a sort, or you must have a hash join, or are performing aggregate type of operations like counts, distincts, and aggregates, is highly recommended. Now, occasionally, as you're evaluating queries, you may come up with a bug in Stardog. And so here we're looking for an ask query that is selecting a count as count, where SPO having a count greater than 1. So looking for just triples and counting them. And instead of having any type of scan or join, instead we have the empty node, which clearly should not be there. Now, in the event that you have found a query plan that you believe is incorrect, Stardog support, either through our official support channel or through our community support, is the recommended way to post your query plan and report the bug. So there are several ways to speed up queries. As discussed, we need to increase selectivity, make sure we preserve the pipeline wherever we can, and make sure that we are getting the data that we want. So first, adding a limit to a query, because quite often we don't need the entire data set, and performing paging operations very similar to relational databases, we're doing limit and offset, is a quick way to page through data. Second, adding an extra distinct without real reason, and minimalizing select variables, not over selecting things that aren't actually going to be used, are good ways to keep the selectivity in place. 3, adding more constants to the query. This provides more selectivity and can help the joint order optimization as discussed. And then finally, split into multiple queries. We can use the subqueries, or if a query becomes too complex, even if its components are relatively fast, we can execute those as multiple queries. You need not have one enormous complex SPARQL query to retrieve all the data at once, especially when the individual piece parts can be done relatively quickly. Now, when reasoning is turned on, query plans will be different. The reasoning feature introduces query time reasoning rewrites for queries, meaning that the axioms from the ontology will be encoded into the query as rewriting the query. Typically, this is going to introduce many unions. For example, if we have a parent class with multiple subclasses and we're going to use reasoning to pull back all of the subclasses, then we would expect things like having a query rewritten with many unions. Additionally, the query plan may contain special reasoning plan nodes that we have not yet discussed. So let's take a look at those. We have reasoning node types for type, which is referring the inferred types of an individual, such as the class example I just used. A property, which returns the inferred properties for an individual. Top, meaning returning all individuals that match. And schema, returning results for schema queries. So we can use our query explain tool with the -- reasoning parameter to see how the query is rewritten when reasoning is turned on. And so here we know that student has some subclasses like graduate student, research assistant, and undergraduate student. And when reasoning is turned on, we see that this has been rewritten so that we union them all together. This completes the section on tools and examples. This concludes the training on performance. Let's review our learning objectives. In this training, we were able to understand capacity and data inputs into Stardog, things like memory and disk space to have optimal performance. We were able to self-diagnose a performance issue leveraging SPARQL semantics, understanding the implication of joins, filters, and optional operations. We learned to read query plans and used to identify performance issues and how to fix them. And we reviewed Stardog's tools and examples for debugging performance issues. Thank you for following along. If you have any questions, please review our frequently asked questions page or head to docs.stardog.com for additional information.